Okay, more RC circuits. Let's talk about time constant. So in all of those exponential functions, we had e to the negative t over rc. So this appeared somewhere in all of those. So this quantity rc, sometimes people just use a tau for that, a lowercase tau. That is called the time constant. Rc or tau equals time constant. So, as you might guess, from the fact that this is a multiplicative factor on the independent variable, if you think back to like algebra 2 and function transforms, if I multiply my independent variable by some number that changes, that does like squash and stretch on the horizontal axis. So RC is related to how fast the changes in the system occur. And the fact that it appears in a fraction with a t, it's t divided by rc as an exponent. Now, exponents, just like the argument of a logarithm or the argument of a trig function, exponents have to be unitless. So the fact that the derivation led to this construction, t divided by rc, that tells us that r times c must be an amount of time. It's not obvious, because r is measured in ohms and c is measured in farads, but nevertheless, ohms times farads is equal to seconds. I will go ahead and write that because it's so weird. But ohms times farads equals seconds. So we know that RC is some amount of time. The question is how much time? Like, what's the significance or the meaning of this time? It can't be the amount of time that it takes for the process to finish, because according to this model, the process like asymptotes, so it takes an infinite amount of time. So it's not just a measurement of the amount of time, because that would be infinite. So you can make an analogy between the time constant and something like half-life, but time constant is trickier in a lot of ways than half-life. One of the reasons it's trickier is that with half-lives, the graph always looks the same. I'll sketch this and I'm going to erase it later, but if I was making a half-life graph, it would have to look like that. You have some initial value, your starting number of radioactive nuclei, or the starting activity count from your Geiger counter or something. So you have some initial amount, and it gets weaker and weaker over time, approaching zero. That is the only meaning for half-life, at least in radioactivity. But when it comes to RC circuits, for one thing, the final value doesn't have to be zero. In the cases that I showed you so far, the final value would have been zero. But it's possible to have a non-zero final value like this if there's like an extra battery in the circuit somewhere or something, such that the capacitor can't ever fully empty. Maybe the capacitor is always going to have some charge on it if it's connected that way. So that's one of the complications. And additionally, in RC circuits, it's not always a decay. You can get growth functions as well. Those growth functions can start at 0, but they can also start at some non-zero amount, like this as well, if the circuit is constructed differently. So that's one of the things that makes time constant harder than half-life to think about. And the other is that because the base we're using here is the number e instead of the number 2, the amount of time that passes when one time constant has elapsed, it's not the amount of time that it takes to go through half of your process. Instead, it's the amount of time that it takes to go through 1 over e of the process. So I'm going to, on the pre-existing graph there, the Q versus T graph, suppose we're doing, let's do a decay first. So if I've got a decay graph like this, I have this initial value, which would be Q naught. After one time constant elapses, I'm going to be somewhere around here. So that's one time constant, or 1 tau. And the amount that I've got is Q naught over E. And I know that that has to be the case because if I plug in one time constant for t, this e to the negative t over rc becomes e to the negative rc over rc, which is e to the negative 1. So whatever my initial value was, I am now at e to the negative 1 times that. E to the negative 1 is roughly 37%, or 0.37. But it's irrational, of course, because it's based on E. So after one time constant, I go from my 100% starting value down to around 37%. That also means that the amount that I have dropped is 63-ish%. So after one time constant, 37% is left, 63% has already died out. Trying to do something clever here. Okay. So that's the decay case. I have copied the graph. Let me draw a growth. Growth is something like that. Again, here I'm starting at 0. So my initial value now is 0. If I go out one time constant, I should be up to 63% of the maximum value. So all I've really done here is like flip the graph over. But the idea is that in this time interval, tau, 63% of the process has occurred, 37% of the process still remains to occur. It has not happened yet. So conceptually speaking, that's what the time constant is about. It's less convenient than a half-life because it's not symmetric. Very, very roughly, you can think of it as like 2/3, 1/3. 2/3 of the stuff has happened, 1/3 is still going to happen. But in these graphs that I'm showing you, again, I'm using 0 as either the starting value or the final value. Sometimes that's not going to be the case. So let me switch to this Desmos graph. I should hide that purple one. Cases that are non-zero. I'm going to send you a link to this graph so you can mess with it. I just want you to think about the one case that I'm showing here right now. So this system, I guess with the values I have here, it's starting at 4. So that could be the charge Q measured in coulombs, or it could be the potential difference of the capacitor in volts or whatever. That doesn't really matter. So let's say it's 4 coulombs is the initial charge. And it looks like I'm asymptoting towards 9 coulombs. So after one time constant, again, 63% of the process has occurred, 37% of the process is left to still occur. But because I'm moving from 4 to 9 instead of like 0 to 9, that does not mean that I'm at 63% of the final value. I've done 63% of the change that I'm going to go through. If I scroll forward, like if I go up to 2, the computer's a little laggy, so it's hard to get it precise. But notice if I go to 2 time constants, the amount that remains is now 13.5%. If I go out to 3 time constants, conveniently enough, I have this set so that the time constant is 1 second. If I go out to 3, now only 5% the process remains to be done. So similar conceptually to half-lives, each additional time constant does less or contributes less to the total amount of progress. The very first time constant, the first time interval, is the most important one where the most change is going to occur. And the steps get progressively smaller. Same time interval, but smaller and smaller steps in those intervals. So again, I'm going to send you the link to this Desmos graph. There's a lot of stuff you can mess with in it. And I think that is all I need to say for this one.